Good morning. Good morning, participants. A very good morning to all. I, Dr. Tejaswini Panse, Electronics Engineering Department from Yashwantrao Chauhan College of Engineering, welcome you all to the third International Conference on Emerging Trends in Engineering and Medical Sciences, Icetems 2026, technically co-sponsored by IEEE Maharashtra section. It is my pleasure to introduce Dr. Shravant Kumar Ramkuri, an accomplished academician and researcher in the field of electronics and communication engineering. He completed his MTech in RF and microwave engineering from Vishakhapatnam in 2012 and earned his PhD in brain computer interface for medical application from Birla Institute of Technology, Mesra. He also completed his postdoctoral fellowship at University of Technology, Sydney under the prestigious RAISE Innovation Grant. Currently serving as an assistant professor at VNR Vignajyoti Institute of Engineering and Technology since 2016, Dr. Shravan Kumar has over a decade of experience in the brain-computer interfaces, artificial intelligence, and biomedical signal processing. He has published 25 plus research papers, contributed 6 international patents with 4 granted patents, and authored multiple book chapters. His research interests include brain-computer interface, biomedical signal processing, sensor networks, neurocomputing, machine learning, and healthcare monitoring system. He actively contributes to the research community as a reviewer for IEEE and elsewhere journals and as a session chair at international conferences. We are honored to have with us today, sir,
Yeah, thank you,
today
madam.
enlightening us, yes, on a plenary talk on the topic AI-enabled brain-computer interfaces transforming medical and engineering application. Welcome you, sir. Over to you, sir.
Yeah, thank you, madam. Thank you for wonderful introduction. Good morning, everyone. Good morning, respective conference members. I'm sharing my screen.
Yes, sir. Yes.
Yeah, is it visible?
Yes, sir. It is visible.
Yeah. Uh, Good afternoon, everyone. Welcome to International Conference on Emerging Trends in Engineering and Medical Sciences, ICTMS 2026. Uh, thanks for my inviting as a plenary talk as a general chair, Dr. UP Wagle sir, and organizing chair, Dr. Prachi Fasadkar, and technical committee, Dr. Prasanna Fasadkar sir. Uh, Today, I will start my present my topic on neural bridge or AI-enabled brain-computer interface. This topic, this research area, is combines neuroscience, artificial intelligence, and engineering. Creates a system where human thoughts can directly control computers or machines. This topic, the brain-computer interface, is a nowadays a very high research area from medical applications and entertainment and research will be starting in engineering perspective. There's a high widely research area for the researchers and those who are going for an PhD or those who are going to the research. This is a best research area for engineering and medical applications. Uh, Myself, Dr. Shravan Kumar Ramakuri. I'm currently working as an assistant professor in Department of AI at Anurag University, and I done my research basically focus on biomedical applications in the research area of brain-computer interface. Today, agenda of basic architecture of brain-computer interfaces and hardware evolution of neural of implants and deep learning techniques for decoding brain signals. Is it audible now? I'm getting an audible or my voice is audible?
Yes, 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 sir.
Yeah, fine,
Yes, you
fine.
are audible.
Yeah, fine. And what are the roles of generative AI and what are the different types of medical applications using as speech and motor neurosciences and industrial engineering applications in the research and the market landscapes and the key players of what are the aspects of nowadays in the research and ethics of governments and future outlook, human AI symbiosis, and the challenges of the roadmap of what are the future works are there. In the conclusion, I will explain. Yeah, coming to the brain computer interface, what exactly brain computer interface is that? BCI is a rapidly transisted or spectacular curiosity of uh, direct communication channel between human brain and the digital computer. And one more can called as a brain computer interface were once considered like I said, a science fiction, but today where there are several technologies to break out through the practical, okay, like a high density neural recording is called, we can record thousands of neurons simultaneously, like high density neural recording is a hardware advances allow simultaneously recording of neurons simultaneously. And the next deep learning architectures, AI can decode as a complex brain signals and the miniature implants like devices are no, we know the extremely small, and bidirectional communication is nothing but the system can read signals and the simulation brain. Modern BCIs both read motor intent and sensory feedback. No, the BCI, sir, can anyone ask like research where we can apply in the BCI as a when you're going to the direct communication channel between human brain and the digital computer, like a assistive wheelchair. In entertainment, we are developing different types of gaming, like a for example, you are all are playing like a Super Mario Candy Crush. In the mean future, we will go for an playing with an Candy Crush, Super Mario, or this type of games for developing using our brain signal only without any muscular activity. Why they are developing as a researcher? Nowadays, humans are degrading their concentration levels using as social media or using as any type of mobiles. They're degrading their concentration levels up to you're seeing as a kids below 5 years to the 13 years. They are drastically degrading their concentration levels using as reels or social media or any other thing. The technology can aspect of advance of research on brain signals. They're designed as touch type of gaming of entertainment aspect, and human can improve their concentration levels and sleep levels. This is a fundamental of motivation of brain computer interface. And what are the architecture? There the next coming to the foundation of architecture and a signal acquisition paradigm. There's a basic loop of BCA architecture is that input realization and signal acquisition and neuromechanism of output interaction. A brain computer interface of four main stages are there. These four main stages of first one is a when we are acquire the raw data from the neural activity of the brain signal, and the second is a signal acquisition. You all know that electrodes capture raw electrical signal to the neural tissue, and third one, A algorithm decode the user interpretation of user intention, and the fourth, finally, we can give as the output as a commands. See this diagram of how we can go for an. We have an acquired raw data from the different wired devices or wireless of EEG devices and capture the raw data from different channels of electroencephalogram is nothing but EEG called as a brain signal using of different types of devices, and this signal acquisition gives the complete time to frequency changing of processing in the signal processing. We will remove the raw like a noise of the device, and we will go for a device interface of assistive device, different types of assistive device like a wheelchair, and we are designing as a virtual keyboard, or we are designing as like a using of internet of things in the home assistance. We can work within a lights off and lights on, or moving chair, or these are type of an entertainment we are developing as a different researchers can develop in a different types of gaming applications. And it will be giving as a loop. coming to the, it will be complete AI and denoise extract intent from the noise, physiological data, and the deep learning models map neural patterns to specific phonons or self-calibrating algorithms and reduce need to daily evaluation. And what are the these types of methods? There are three ways of capture brain signals. First is the invasive, as these were the very very beautiful diagrams of what are the invasive, and partially invasive is the second one, non-invasive is the third one. The invasive is the electrodes are implanted directly into the brain. When you are seeing the latest researchers can develop as a neural link or the direct implant of the electrode into the brain. The partial invasive, that electrodes are placed right the surface of the brain, and non-invasive is nothing but it's devices like EEG caps. Like nowadays, we are using non-invasive wireless EEG caps. Like different types of companies or their emotive muse or these type of devices can work that gaps of the measure the signal from the outside of the skull. There are safer but lower signal resolution uh, compared to the electrodes implant directly into the brain. It will be high signal quality but require the surgery. It will be takes first one invasive is a completely we required once human surgery. It will be takes to directly implant as a data. What are these invasive and non-invasive methods are there? We researchers can thinking about that human brain data can capture, and when you're saying the data of the brain signal, and we will work within a direct researcher can work within a brain data to multiple different type of activities. The previously no, the research will be invasive, more invasive methods like modalities of there are micro errors, and these are all differences between invasive, partial invasive, and non-invasive. There are interconal microelectrode errors like Utaria or Neuralink. Partial invasive is called electrocardiography, ECOG, as a very functioning as a muscular movement of and a signal technology is called non-invasive electroencephalography and MEG. Or whether we coming to the signal fidelity is a low resolution from the signal attenuated and scalene scalp, and we're coming to the partial invasive and coming to the invasive highest spatial temporal resolution, coming to the direct implant of the sensor into a brain. Okay, these are all three methods. Though now their researchers can working at the working as soon as we are coming to the 2026 era. The mainly brain will be as a wireless transmission or wireless devices are there in the market. There are different types of wireless devices. Are those who are going to the research, search in wireless EEG devices in the market, like in a main thing of emotive, muse, neurosky. There are different types of biocap. There are different types of examples are there for uh, coming to the starting with the research. And what are the spectrum for scalp to synapse? Like a invasive is a intracortical microelectrode or ARAS neuralink or captures individual action potential requires neurosurgery. It will be complete implant the sensor into your brain. Like partial invasive, like is a muscular movement, avoids crossing the blood brain, the lower surgical risk. The non-invasive, you are looking the like in the diagram, the one of the subject will be handled like movement of right and left movement of moving as like a biocap, and it will be different types of sensors, 14 sensor, 21 sensor, depending on the development of EEG sensors, and signals attenuated by the skull, high safely profile, ideal for the consumer neuroganic large scale of the screening. Now the research will be going within the non-invasive model. And what are these uh, neurosignals and types of brain rhythm? Okay, we are acquired the data. We have acquired the data from the different types of devices. What are these reasons? Coming to this diagram, there are the researchers can design and define from the when capture the raw data from the time, and we are changing into a time series data to the frequency for carrying for an information. There are different types of bands. Delta is a 0 to 4h. Every human body, every human brain or human biological body, it will be gives the below 100 hertz frequency, and it will be defined from the extraction of the features coming to these frequencies. There are different types of frequencies. The brain produces electrical oscillations called brain waves. Delta is a very slow wave. When we are finding to sleep, dreaming, in the person will be dreaming, or when your person will be asleep, the data will be occurred. Theta is a drowsiness. Mainly this delta and theta, when you are going to the 4 to 5 years below of the kids, it will be affected of delta and theta, and alpha 13 to 30 hertz or 8 to 12 hertz, sorry, it will be restful or reflectful, and beta will be 13 to 30 hertz. It's a very active mind. When you're playing a game, when you're working, when you're watching a movie, when you're studying, these beta wave will be occurred. I'm not considering this. I'm not giving us these values. These are the standard values. This is how researchers can done in the previous 20 to 30 years. The EEG of the brain signal will be starting at the 1924. Hans Berger is created the captured one first time of the brain data. Then these recordings of these data, depending on the extraction of their researchers or features, it will be affected. Okay, these are all how to capture and how to the raw data are captured and acquisition of the raw data and feature, the frequency band of the data. Like, what are the decoding pipeline, like what are the decoding? Brain signals are extremely noisy, the brain signals are non-stationary. It will be very noisy, and they are the following the steps are there. The signal processing will be initially processing the
Sir, you are not audible. There will be technical issues. Sir will be joined within 2 minutes.
Yeah, is it audible right now?
Yes, sir, you are audible
Fine,
now.
fine, fine.
Please share your PPT.
Just, yeah, I'm sharing screen. Yeah, is it visible?
Yes, yes, sir.
Yeah,
It is
fine, fine.
visible.
Thank you. Yeah, sorry, there's like a small technical problem. Coming to the like hardware evolution, now the technology can rapidly growing of what are the things of in early BCS devices were large and bulky. In the previously in 1924, the devices can be very large. It will be comes to the 1 hour to 2 hours from 1 hour to it will takes the 4 to 5 hours to take a raw data from large wild devices. Like recent innovation, we have allowed the single chip neural implant. Like we will thousand of electrodes to extremely small size. The traditional implants were bulky, consisted of electronics. Of the modern standard chips of the single chip of and minimize the entire BCS system of these 65,536 electrode integrated on a single chip and simultaneously recording channels of entire wired devices entity simple. You are seeing as a innovation from the past 100 years of from laboratory curiosity of the convergence of biological systems and computational frameworks from in the laboratory curiosity to the consistence of modern neurophysics, a fundamentals of re-engineering of human interaction via direct neural translation. It will be high speed wireless communication and extremely small size. Like one modern implant can integrate tens of thousands of electrodes on a chip, only a few millimeters in size. It will be high resolution neural recording and faster data transmission and lower power consumption. This you are taking as a single chip CMOS integration eliminates the physical bottlenecks of the traditional brain implants. This traditional implant relied on a bulky consist of electronics, and the modern standard of shifting to single chip solutions like the research will be work done by Columbia University Biological Interface Systems, the Cortex as BAC, as it will be completely uh, like thousands of electronic circuits will be coming to the single. The platform supports its communication via 16,384 channels from the real time write operations. Oh, it will be very very fast and transmission of communication and scaling of hardware by a single chip CMOS integration, moving away from the bulky consistence of the BSC biological interface system to Cortex. This is extremely miniaturization, 3 millimeters of thin of 50 micrometers of unexcelled bandwidth, 100 Mbps of ultra wideband ratio of radio link, and 65,536 electrodes and 16 phase simulation channels. It will be rapid growth in the sector of brain signal acquisition. Okay, there are several electrode technologies currently in the market. There is a Thare and widely used in research, and it will be specifically 100 electrode, 10 to 10 French wave, and 1.5 millimeter depth, and a gold standard for research and brain gate trials of thing. And Neuralink is a flexible thread based electrodes and third one is a synchron strain rod is nothing but inserted through the blood. Strain rod is nothing but endovascular stent and 16 electrode and minimize and invasive and moving toward the trials. And cortical interface or is nothing but vessels surface level of interface is called specs of 2048 interval based on the brain surface. There are several electrodes technologies and currently used in the market. There are the 100 or 2 of million funding of cortical interface of circuit, and each technology balances signal quality and surgical risk. And what are the one major challenge of transmitting neural data wirelessly? There is called ultra wideband communication and wireless power transfer and on-chip compression. When you're going to the wireless transmission, there are different types of drawbacks or cons are there, and fully wirelessly and battery free operation is the ultimate goal current operators navigate when you're going to the I'm in my past research in wired device it really takes setup for 45 to 1 hour, and when you're going to the wireless device it will be takes 5 minutes of time for set up a device and capture a brain data. This is the main moving speed of wireless transmission of implants of the BCI, and on-chip compression and thermal safety. And next, edge AI processing, local interference on implant chips reduces the data rates by processing signals before the transmission rather than streaming data. And closed loop elimination, there are the real-time feedback enables implant to respond to detect neural state within the milliseconds. The one thing I suggest that wireless devices are more accurate of data, and but drawback is that the like erroring of this packet of noise removing and power transmission, wireless power transmission is a, and on chip compression is a very key points from the wireless transmission. And what are the next level of deep learning architecture for neural signal decoding, and why deep learning replaced by classical machine learning, that the traditional machine learning methods like we are using of SVM or LDA struggle with brain signals because brain signals are very noisy, non-stationary and high dimension. Deep learning models like automatically learn complex patterns and achieve much higher accuracy. Coming to the moving, when you're thinking about, suppose I'm capturing, when your person is reading a book, suppose at the same time person will be reading a book and thinking about other things also. There the brains is a moving is a non-stationary signals. I don't identify that simply person will be reading a book. Then the complex form is that the signal will be captured and it will be coming to the very noisy signal. The neural signal will be very noisy, that low signal to noise ratio, and we have to give an extract the features. There are different types of deep learning methods where the researcher can using as feature engineering from automatic and hierarchical and non-stational signals adapts via online learning, and high dimensional data handles natively, and inter-subject variability like transfer learning across the subject. You can compare with the classical LDA, limited up to 50 classes and per subject calibration and computational expensive very high, and the requires retiring and 97% point sustained accuracy will be the decoding of using as a deep learning methods. Like convolutional neural network coming to the main aspect in a deep learning methods, treat as a EG signal like images. Like when you're capturing a reading a book, when you're capturing a understanding of CNN is a multi-channel neural data as 2D grid and one dimension for time and one for electron, and learning at the spatial filters and spatial relation between electrodes and temporal front over time. This is a one popular of each design, specifically signal classification. Like when you're filtering as a taking as a capture from the video, when you're going to the recorded a EEG signal from moving driving a car, attention of driver when you're reading it like recently we have in a project drowsiness of a driver will be attention moving of a using other brain signals. When you are applying the CNN, it will be more giving as a more accurate data, and it will be giving in the deep learning models will be uh, the advanced stages of neural networks of using of EEG signals and applying for any type of project. And next, we have going to the transformers analyze long sequences of neural signals. Like there are use of attention mechanism focus on important signal patterns. And recent studies have achieved 97% of space signal from the brain. Like we have the standard transforms 97% ALS patients. Like one to word vocabulary. Like we recently designed virtual keyboard, we observe that these transform analyze long sequences of neural signals will be very high accuracy patterns. And LSTM is one of the networks of the time-dependent patterns. They are widely used of early BCA tasks of the handwriting, decoding, and when you're a paralyzed patient or assistive, we are designing a virtual keyboard. I need some water. He or she has not given to the. I need some water. It will be takes. We are applying the. There are varieties for task handwriting, decoding, and however the slower modern to the transform architecture, like a sequential memory of past neural nets and effective of handwriting and gesture decoding, and lower compressed comes than the like transfer like handwriting of BCA accuracy, like a 26 letters plus space of words. It will be cannot paralyze of introduce of latency and struggle with very long sequences. Like what is a hybrid CNN and transformers? Word accuracy of comparison really going to the standalone CNN, it will be giving us a 65%, and we on the research on the standalone transformers, it will be gives us a 93% of hybrid CNN. It will gives up to 98 to 99 percentage, and it will be hybrid CNN transformer solving accuracy of latency of trade-off. And next, the coming to the next area of up to 2026 to 2035, the generative AI and advanced signal processing techniques is the next we explore improves the BCI system, how generative AI models will be using as in a BCA system within medical and non-medical applications. First thing is the variational autoencoders. VA is of key points of remove the noise from the EEG signals. These noisy EEG of 128 channels encoder network and latent space of decoder net and reconstruct the clean signal. They compress signal into a latent representation and reconstruct the cleaner signal. And it improves mainly decoding accuracy, data augmentation, and subject transfer. And the data transfer to brain is mapping is very key point of using of variational autoencoder. It helps remove noise from the EEG signal. They compress the signal into a latent representation and reconstruct the cleaner signals. Completely, it will be decodes or decoding accuracy will be improves. And next we can go for an diffusion models. Diffusion models generate the synthetic neural data. This is a useful for because collecting brain data from patients from extremely difficult data, and data sets help then train AI models is more effectively. Like rare condition training, generate training of examples of ALS and Locked-in syndrome and post-stroke patients where real data collection is very difficult. And we these diffusion models can help generate the normal EEG pattern, real size data, and like synthetic baselines of privacy and preserving data sets. And what exactly generative decoding is? Traditional BCI uses limited command sets. Modern generative models allow open-ended communication. This is main advantage for using traditional BCI to the modern generative models. Instead of selecting from a menu, users can generate natural language. It will be useful for open-ended natural language output and 1,25,000 words vocabulary and transform learning across users and low cognitive effort, think naturally, and voice learning preserves personal identity. These traditional BCAs of map from the uh, various applications of there, and there are different types of medical applications. There are the speech neuro synthesis, or it will be BCA can restore speech for patients who lost the ability to talk. This is our main key applications for no researchers are working in the speech neurosynthesis. Any researcher can work in the area. BCA can restore the speech from the patient who lost the ability to talk, and neural signals from the speech areas the brain are decoded and converted into synthetic voice. And recent studies, there are the 97.5% word accuracy is there in continuous testing, and it's a directly consortium of developed a streaming brain to voice system. Recent research in the citation I given. And next. Uh, motor neurophysitic, or this is a BCI can control robotic arms for paralyzed patients. There are you can use this recent survey. One of the in German scientists can develop motor cortex signals are decoded and translated into robotic movement. This AI decodes intent arm and hand movements from the motor cortex signals. Self-adapting decoders handle the electrode drift and neural plasticity over months, and sensory feedback and multi-electrode cortex of the create and translate precision and clinical significance. And next thing, AI voice cloning, restoring personal identity through sound. AI voice cloning is a can recreate a patient's original voice using old recording, and this preserves personal identity while restoring the speech. There is one of the next research can going from the AI voice cloning of the personal identity to the sound. And next is seizure monitoring, neural monitoring or seizure monitoring. BCI can monitor brain activity continuously, and AI models can detect seizure patterns and trigger simulation before seizure occur. Okay, this is one of the medical application. Recent of medical application researchers can work. These are all working as the researchers. There are different types of papers you can search in the area, and BCI are transferring epilepsy scape through the closed loop system that detect and size of the frame. And next, go for an industrial applications and AI-driven human robot interaction and Industry 5.0 environment. BCI can help human control robots using brain signals. There are also monitor worker fatigue and cognitive load, and it will be LLM powered covers and neuro monitoring and mental command interfaces. And AI driven human robot interaction will be a key role in the next coming 5 years. Next, aviation, the monitoring cognitive load in a real time, and there are things of their passive BCIs of the continuously monitoring of mental state of cognitive load, and 98.5% of accuracy decoding of the passive BCI can monitor pilot attention levels. Like the nowadays we are seeing of in aviation. This is the next area for the research how air traffic control and BCA using brain control signals and detect control fatigue before errors of the providing oversight without interrupting workflow. Another like another research and another very good research in the aviation. There are consumer applications. Neurolearning includes adaptive learning in systems and stress monitoring devices and brain control gaming. Okay, here the adaptive learning system, mental wellness and monitoring, and smart office environment, and gaming and VR, virtual reality, and automotive safety, and allied athletic training. The non-invasive VEG enable new category of consumer applications. There are the market landscape. We have several companies are like actively developing BCI technology, like Neuralink and Synchron and BlackRock Neurotech and Precision of Neuroscience. These are all working within a market landscape. And next, investment in the investment landscape, over $2 billion have been invested in neurotechnology startups since 2020. These are all companies can investment in a landscape. There are Neuralink, Synchron, Precision Neuroscience, and Caron, and Control Labs, and Brainco. These are all backed by Elon Musk first human trial ongoing, and Synchron is a strategic partnership of with Apple and Nvidia, and reversible of cortical interface of surgical co-implant strategy, and Kernel is a non-invasive flow helmet of for FNIRs based monitoring and acquired by Meta, and Brainco is a consumer EEG for training of prosthetic. Okay, and coming to the ethics and BCI become powerful and ethical issues emerge of mental privacy, identity protection, and fairness in access. Okay, these are all era of mental privacy and neuroscience side of ethics of and regulations. There are some regulations. Some countries are already developing legal frameworks of the neural data. How the rules and framed introduced Chile introduced like neuro rights laws recently, and algorithm bias. BCA system must work across diverse populations. Training datasets must include and the brain patterns and the future human AI in the symbiosis by 2035. BCA may enable continuous interaction between humans and AI systems. This continuous human AI system will be BCA could enhance uh, cognition by expanding workout memory and enabling through the computing based computing. BCA could enhance by human by computed by the memory and enabling through the based computing. This by 2035 continuous human AI symbiosis fundamentals of altered society. And somewhat examples are there. There are future environments may respond automatically to mental states, and there are the technical challenges. Artificial intelligence of the smart interview are what are the smart several challenges of adaptive recording algorithms on long-term implant safety and neural data, and the challenges of path development roadmap for the technology from the roadmap and November no 2026 feasibility proving and clinical expansion and commercial scale and symbiosis era. We have in a 125K word speech BCA in 7 months stable motor control and multi-patient powered trials, and there's the 29 to commercial scale, and there's a symbiosis era and the three pillars requirement: the uh, practical AI decoding algorithms, neural data security, global safety standards. Okay, these are all points and key takeaways. And BCAs are no longer speculative of the boundary between human thought and digital technology is completely going through the deep learning enabled layers and generative AI model and hardware as a software and government must mass development and 2035 realistic horizon for symbiosis. And uh, coming to the conclusion, I'm giving as a conclude by the boundary between human thought and digital technology is disappearing. Our responsibility is to this technology is safe, ethical, and accessible to everyone. Thank you for this session. Moving to technical committee.
Yes, any questions from participant? Sir, I have one question. What are the major challenges in decoding brain signals?
What are the madam? What are the
Challenges.
Yeah, actually, the challenges are mainly we. I observed that the brain is a non-stationary signal. We are giving to the data with a, black chamber room, and it will be coming to the when you're taking it the multiple iterations when we are taking the raw data and observe the every human have a different scalp, and it will be gives of a different types of devices can be work human researchers can be working, but the based on the human brain, based on the every human brain have a different strategic, and every human brain has a different non-stationary path, and the observing that acquiring raw data is a more difficult for preliminary stage. The previous wired devices are giving as a time delay, but it will be no researcher can be wireless. It will be very time consuming, very low, but the limitations are there and cons are there right now. Acquiring data is more difficult right now.
Yes, sir. Okay. So, thank you so much, sir. On
Yeah,
behalf of entire conference team, I would like to extend our heartfelt gratitude to our esteemed guest for taking the time to join us today. Your presence and valuable insights have made this session truly enriching. Thank you. Thank you, sir.
yeah. Thank you so much, madam. Thank you so much. Thank you, organizing committee, for inviting me. Thank you so much.
So, dear participant, you have your sessions from 2 p.m. Thank you.